Okay, so we take an example of absolutely continuous random variable. So let x be an absolutely continuous random variable with a PDF. Okay. Okay, so the PDF is described with a parameter C here. And you can justify that for x in this range, this value okay, so this value is always non-negative. Okay. Now the question is, what is C? Okay. So what is C? Right now, since the probability of the total event is equal to 1, okay, and this is equal to this event, right? And by the definition of a PDF, so we know that this integral must be equal to 1. Okay, must be equal to 1. And so that, and by the definition of this PDF, so that it's 0 outside of this interval. So which means that this is equal to C 4x minus 2x squared dx. Okay. Okay, and now you can evaluate on this integral. You can evaluate this integral. And you find that this integral is equal to, okay, it is equal to 8 over 3. Okay. All right, so we have an equation that C times 8 over 3 equal to 1. Okay. So that C equal to 3/8. Okay, so it's 3/8. So we find C exactly here, and we can also to find the probability of the event. Okay, the event described by the random variable x. All right, so we know this is actually x in what? 1 to infinity. Okay, so the interval is bigger than 1. And so by the definition of so we know that this is 1 infinity. Okay, so this is 1 to infinity f of x dx. Now again, f of x is here. All right, and it is 0 outside of this interval. So we know this is equal to 1 to 2. And we know C is 3/8. Okay, all right. So the integration is from 1 to 2. Okay, from 1 to 2, and you can do the integration, and you'll find that this is 1/2. Okay. So the probability of this event to occur is equal to 1/2. Okay, it's equal to 1/2. So we find here. Okay, so usually to find probability or related problem, with an absolutely continuous random variable, you usually use the integral calculus of one variable if we consider a single absolutely continuous random variable here. Any questions for the computation here? All right. Now, so for an absolutely continuous random variables that we can compute the CDF by a PDF, right? So as we know, so for an absolutely continuous, I use AC, a random variable X with a PDF, f of X. The CDF, the cumulative distribution function, f of X of random variable X can be computed. As here, so you know f of A, which is the probability of the event that random variable has value less than equal to little a. So this is equal to, okay. Right? And because that the CDF is an integral of a Riemann's integrable function f of x on the real line, and so we know which is a continuous function. We know that. Okay. All right. So now we want to. So we, because of this relationship, the CDF is expressed as an integral of a Riemann's integrable function, little f of x. All right, so they should have some relationship from calculus. And so we recall the first fundamental theorem of calculus here. So let G be a real valued function on a finite cross interval AB, which is Riemann integrable over AB. Okay, so suppose we have a Riemann integrable function G, okay, defined on a finite cross interval A to B. Now define a real value function on AB, okay, by an indefinite integral. So this is from A to X. G of t dt. Okay, so we define a new function. Okay, expressed as the indefinite integral, all right, of the little g function here. Okay. Then big G is differentiable okay, at each x in the open interval AB, right? So x in the open interval AB. Where G is continuous. Okay. So, because that the big G is an indefinite integral of little g, okay, and so a conclusion of the first fundamental theorem of calculus is that the big G is differentiable at each point x in the open interval where little g is continuous. Okay, so when the integrand little g is continuous at a point x, then the big G is differentiable at that point. Okay, and the value of the derivative of big G at this point x is equal to the little g. Okay, so this is the result of the first fundamental theorem of calculus. Okay, so when you learn calculus in your freshman year, you should know, okay, this first fundamental theorem of calculus here. Any questions about the statement of the first fundamental theorem of calculus? Okay, and so the first fundamental theorem of calculus tells us that if a PDF f of x of an absolutely continuous random variable x, right, is continuous at x equal to a, then the CDF f of x of random variable capital X is differentiable okay, it's differentiable at x equal to a, and we have f prime of a equal to little f a. Okay, and how to show this result? Because that, as we know, that okay, so we know that if the a PDF f of x is continuous at a, right? At a. Okay, and so we let C and B here. Okay, so we can select CB there. Okay, and define. Then f of x is Riemann integrable over CB. Okay. Why? Because as a PDF, we know that f of x is Riemann integrable over the whole real line. So of course, it is Riemann integrable in a subinterval of the whole real line. Okay. We have said since f of x is Riemann integrable over CB, and we know f of x is equal to f of c plus c and this is equal to which is equal to f of c plus for all x in C and B. Okay? i.e. f of x minus f of c equal to cx right, so we have that. The little g here in the first fundamental theorem, okay, the little g is just like the little f here, okay, because little f is Riemann integrable. And the big G here is just the difference, f of x minus f of c, right? So this is the so you can think about that. So this is our big G, and this is the G of t here, okay, in the first fundamental theorem of calculus. Okay, all right. So all the required conditions are satisfied, right? Okay. right? So by the first fundamental theorem, the first fundamental theorem of calculus, okay, f prime of x minus f of c is differentiable at x equal to a and okay, is equal to f of and the derivative at x equal to a is equal to f of a, since f of x is continuous at x equal to a, which is in CB. Okay? Because the point A is in the open interval. Okay? Just here. Okay? So now this function is differential because this is fx minus a constant. So we conclude that f of x is differentiable at x equal to a, and f prime of a is equal to f of a. Okay. All right. So this result is that if we are given a PDF, then we can know the differentiability of the CDF. Okay, from the first fundamental theorem of calculus. Okay, and this result shows that the CDF is differentiable at a point where a PDF f of x is continuous. Okay, so that's why because we have infinitely many possible choices for a PDF, right, of an absolute continuous random variable. Right, so we usually select a PDF which is as smooth as possible. Okay, for example, which is continuous. Okay, which is continuous, has continuity in an interval of or a union of interval of in the whole real line. Okay. Okay. The other direction is that how do we know? So how do we know that a continuous random variable x okay, is absolutely continuous. All right, so the question is that. So how do we know that? A given continuous random variable is absolutely continuous. Okay. All right, and part of the answer, okay, is by the second fundamental theorem of calculus. Okay. So let's state the second fundamental theorem of calculus. Okay, it's kind of review of the main result in calculus. So let little g be a real valued function on a finite closed interval AB, which is Riemann integrable over AB. Okay. Now let big G be a real valued function on AB, which is continuous on the closed interval and differentiable in the open interval. Okay, so it is continuous on the closed interval, but only requires differentiable in the open interval. So we do not ask for the one side derivative of the big G function. Okay, we just need that G is continuous on the closed interval. Okay, so it has the one side continuity here. Okay, but for differentiability, we just require it in the open interval. Okay, and so that the derivative of the big G is equal to the small g for all x in the open interval. Okay, we just need that. Okay, then the relationship between the little g and big G is here. If we integrate over g, little g here, okay, because we know the little g is Riemann integrable, so this integral exists and finite here, and so this is equal to big G prime of x. Okay. All right. Now we know the G prime defined only on open interval. Okay, but for integration, that we know that because our differential here, d of x, you know that because of this specific integrated is linear here. So at a point, a single point, the integral is 0. Okay, so that's why, as we know in calculus, even though the G-prime function exists in open interval, okay, even that is in open interval, but we still is able to evaluate the integral here with the lower limits is a and upper limit b here. Okay, all right. So these two are equivalent, the same. Okay, and it is the difference. All right. So the important thing is that the second fundamental theorem of calculus is that we can recover the big G from the integration of little g. Okay. Okay. So this is the second fundamental theorem of calculus. Any question about the statement here? The reason why we need a little g is that the derivative of big G exists in the open interval. Okay, so we do not ask for the one-side differentiability at the endpoint of this closed interval. For big G, we do not require that. We only require big G is continuous on the closed interval and differentiable in the open interval. Okay? Okay, so the differentiability here is defined by the two-side derivatives. Okay, the usual definition of differentiation. Okay, all right, and the little g is actually even though they are equal, right? But the little g has a value at the two endpoints. Okay, so little g is defined at both endpoints. Okay, so you can think about that the little g it is based on the G prime, but you give values for the two endpoints A and B. Okay, here. Okay, so you can see here. So this is the second fundamental theorem of calculus. All right, so now we need a definition, a real valued function G on an interval I in the real line. So the interval I can be finite interval, half open, half closed, or maybe semi-infinite interval, just arbitrary interval. Okay, so a real value function on interval I is called piecewise continuously differentiable. If for each finite subinterval AB of I, there are finitely many points A sub I in AB with A equal to A0, this is A1, this is an minus 1, less than an is equal to b. Okay. Such that G is continuously differentiable in each open subinterval, okay, from I minus 1 to I for all I. Okay. So in each piece, all right, in each piece here, in each piece, the little g function has continuous derivative. So its differentiable means that g has derivative, and this derivative is continuous functions. Okay, so that's why it's called, we call continuously differentiable. Okay. An example is here. Suppose that we have minus 5. So that this is g of x, and you can think about that. You have A1 here, A2 here. All right, and so you see that Gx continuously differentiable in mass 5 to A1 union A1, A2 union A2 and infinity. Okay. So in each piece, in this piece from mass 5 to A1, G is continuously differentiable. And in the open interval A1 to A2, this function, G function, is continuously differentiable. And in the interval from A2 to infinity, the G function is also continuously differentiable. Okay. So from here, so that G is piecewise continuously differentiable on mass 5 to infinity, okay, on this semi-infinite interval. Okay, so this is just an example, as you can see here. We can make a remark here. If G is a piecewise continuously differentiable real valued function on an interval I in R, then G is not differentiable. Okay, only at countably many discrete points in I. Discrete point means that so A1 is a discrete point. Why? Because in an interval, okay, in a very small interval, so this is A1 minus epsilon, A plus epsilon. In here, there is only one point which is not differentiable. It's called discrete point. This is also, okay. So this point okay, which means that there exists. So then there x and epsilon within 0 such that g of x is differentiable in ai minus epsilon, ai plus epsilon. So g of x is differentiable in this very small open interval around the ai, except that x equal to ai. Okay. So it's called discrete. Okay, so you can at a neighborhood, in a neighborhood of ai, okay, the function e to g is differentiable, except this point ai. Okay, so it's called discrete point. And so they are, so if g is piecewise continuous differentiable, all right, on an interval I, then g is not differentiable, okay, only at countably many discrete points. Okay, right? So because for any interval, it's an union of finite subinterval, right? And in each finite subinterval, you have finite many discontinuity point which that g is not differentiable. Okay, so you take the union. Okay, you take the union and you see here. Okay. So for example, let me make a. So you can divide, for example, I is just the whole real line. Okay, and so you can okay. So this is n to n plus 1, etc. Okay, so R is the union n from minus infinity to infinity of n and n plus 1. Okay, so the whole real line is, you can see that, is the union of the finite closed interval, and it's countable, right? Of many. Now in each n plus 1, they are finitely many. They are only finitely many points in n plus 1 where g is not differentiable. Okay. So for each interval, there are only finite many points that g is not differentiable. And so the union, the set of all those points for all n in Z is countable. Okay, so that is countable. So we now write a theorem, okay, a proposition. If the CDF f of x of a continuous random variable x is piecewise continuously differentiable on R, then so if the CDF of a continuous random variable x is piecewise continuous differentiable, then x is absolutely continuous with a PDF f of x, which is equal to f prime of x at those points where the CDF is differentiable. And can be assigned to a non-negative number at those points x where f is not differentiable. Okay. So a sufficient condition for a continuous random variable to be absolutely continuous is to look at is a CDF. And if the CDF is piecewise continuous differentiable on all, okay, then that the random variable X is absolutely continuous. Okay, so this is give. Okay. Because capital F is the CDF of a continuous random variable, so the capital F, this CDF is a continuous function on R, of course. Okay, this is the basic things you have to know. And if we know this continuous function, capital F of X, is also piecewise continuously differentiable. Okay, then we actually know that the random variable X is absolutely continuous, and we can find the PDF for that. This PDF X is equal to the derivative of the CDF F prime. Okay. For those point X where the CDF is differentiable, but if F prime of X does not exist, all right, then we can assign an arbitrary non-negative number to F of X. Okay. Okay, and the proof. Okay. So I think to save time, then I will give you a lecture note. Okay, and the proof, of course, will use the second fundamental theorem of calculus. Okay. 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 So this proof is based on the second fundamental theorem of calculus. So let's take a break, okay, up to 22. Okay. Okay, now let's look at a special type of absolute continuous random variable. Okay, so a random variable x is called uniformly distributed over a non-empty finite interval AB or curves interval AB if it is absolutely continuous with a PDF. This PDF is specified. It's a constant 1 over b minus a. So b minus a is the length of the interval. Okay, for a. And the 0 otherwise. Okay, so the PDF looks like here. And this point is 1 over b minus a. Yes, please. Yes, that's fine. All right. Or good. Yes, that's good. So yes, good. Right, so this is in particular for closed interval. But it can be defined for half open, half closed interval. Thank you. Now the CDF of x is 0 if x less than a, but it's x minus a divided by b minus a for a in x b, and the 1 with x greater than or equal to b. Okay. So as we have shown before, an absolute continuous random variable has infinitely many PDF. Okay. So we say that x is uniformly distributed. Well, if we can, this random has a PDF with this form, right? But actually it has infinitely many other PDF, right? Okay. So at the endpoint, actually you can specify an arbitrary non-negative value. Okay. So that it's fine, just here. Okay. But for CDF is unique. So even though PDF can have infinitely many possible choices, but CDF is unique. Okay, so you can see this is the, and so the corresponding would be, this is A, this is B. So this is 1. So it's go this way and go up linearly. Okay, so this is f of x. Okay, so this is the CDF here. And you can see that this is CDF, okay, which is continuously differentiable. Okay, it's continuously differentiable everywhere except at x equal to A or B. Right? All right, so you can see it has 0 derivative, okay, from minus infinity to up to A, but not include A. Okay, and so you can see f of x is continuously differentiable in minus infinity to A, union AB, union B to infinity. Okay. So that thus f of x, it's piecewise continuously differentiable on R. Okay. Okay, so the CDF satisfies the condition of the proposition 5.1.d. Okay. So so you can see that from the CDF, you can see that it is linear in certain interval. Okay, linear in certain interval. Okay, so, and before endpoint A is 0, after endpoint B is 1. Okay, it's 1 because this is the CDF. Okay. And according to proposition 5.1.d, that we can find derivatives. Okay, in each piece where the CDF is continuously differentiable. Okay, so as you can see that in the open interval AB, that this is exactly the derivative of f of x, right? In this open interval. In other interval, okay, it's 0. Okay. Oh, by the way, I'm sorry. Yeah. This is correct, but this is better. Okay. And at the point when x equal to A or B, you can assign arbitrary non-negative number. Okay. So you can assign 0 or 1, or this number is arbitrary. Okay. But as we see that according to your problem, you may want to specify a PDF that this is equal to this value when it's in this open interval, closed interval, or half open, half closed interval, according to your need. Okay, according to your need. So you have some arbitration here. Any questions about uniformly distributed random variable? Okay. All right, another example, interesting example is here. So let x be an absolutely continuous random variable with a PDF. All right, here. Okay, so I use the subscript to denote that this is a PDF of this absolutely continuous random variable capital X. Now let y to be 2 times x. Okay, so it's the double, so that you can see y is obtained by data processing of the random variable x there. Okay, this one. All right, and so the question is that is y a random variable here? If yes, okay, is it absolutely continuous? Okay, we may further ask for that. Okay. And the answer, so we will answer this question in next question, in next section. So this, the answer yes. Okay, has to be justified in the next section. Okay, so we will justify that. This is the answer is yes. And so if yes, what it is absolutely continuous? Okay. Now, if we can find a PDF, okay, for y, if we can find PDF for y, then no problem. Then the y is absolutely continuous. Okay. So to find them, so we look at the CDF of random variable y here. So that by definition, okay, right? So this is so that the CDF of capital Y is the probability that the random variable capital Y is less than or equal to little y here. But as we know that capital Y is 2 times capital X, so that we know this is, okay, it's here. And because capital X is an absolutely continuous random variable with a PDF, so by definition, so this is actually okay, is this one. All right, and by the change of variables, okay, we can, so that's So we let t equal to z over 2. So this is become 2 minus infinity y, and this is z over 2 to here. Okay? All right, and so finally, 1/2 see here. All right, so the CDF of capital Y, all right, express as that the integral from minus infinity to little y, with the integrand here. Okay, so from this, we define a new function f of y to be 1/2 of x y over 2 here. So we define, okay, and we know which is non-negative and remain integrable over R okay, so we have a non-negative and remain integrable function R. Okay, and from here, okay, so since f of y into y is equal to 1 minus infinity of okay, for all y. Okay. This function is a PDF of y, and then y is absolutely continuous. Right? So we find a PDF of y directly from the change of variable here. Okay. So this is change of variable, and once we have a PDF, then of course the random value y is absolutely continuous. Okay. Okay, so we have to answer this question, okay, about data processing of a random variable. Okay, and the title, okay, I use the title in the textbook. It's about expectation and variance of random variable. Okay, so we will consider expectation variance of a general random variable. Because in chapter 4, we have discussed the expectation variance of discrete random variables. Okay. And before we discuss the expectation variance of random variables, actually we discussed the function data processing of discrete random variables. And we have a very general proposition says that actually the function, the data processing can be any arbitrary functions. The only requirement is that the domain of the data processing function contains the range of the discrete random variable, right? So this is very general. But how about a general random variable? Not just discrete, just arbitrary, including continuous random variables, okay? Or not discrete, not continuous, right? It's just an arbitrary random variables. So we have to answer that questions. But before we state some results, so we'll review something, all right? So by proposition 4.1.b, okay, a real valued function x from the sample space, okay, to the set of all real number. So on the sample space, is a random variable, okay, if and only if for any interval I of the real line the event that the value of the random variable is in this interval I is an event of interest in the sigma h by f. Okay. Okay, so this is the way, because by the definition of a random variable is that a real value function on the sample space is a random variable. If the event, if x in any Borel set B must be an event of interest in F, right? But we can weaken the condition here. Just consider only intervals. Okay, that would be enough. Okay, so if this is true, right, for any interval, then if we replace I interval by any Borel set in R, then x in B is also an event of interest in F. Okay, so that is the statement of proposition 4.1.b. And we can further weaken the condition in the proposition. Okay. So in this here is that a real valued function x on the sample space x is a random variable if and only if for any A in R, x greater than A is an event of interest in F. Okay. So this is just very special So we only check intervals which is of this type. Okay, so it's a semi-infinite interval. Okay, starting from A to infinity, and this open interval. Okay, and the proof is here. First of all, we have quite a few types of random variables. Okay, so one, you can see that. All right, so this one is a semi-infinite interval, but it's closed, right? And so this is actually greater than or equal to A. And this one is the, oh, by the way, okay, this is equal to x less than A. X less than A is the complement of x greater than A, okay? It's the complement of that. So of course, so if x greater than A is an event of interest in F, then the complement of this event is also in F, okay? Because a sigma algebra has three properties we listed before, okay? All right, so because this is 1, is there, this implies that x greater than or equal to A is in F. Second, the type that okay, and this is the intersection of, so this is equal to x greater than or equal to A. And so this is the intersection of n from 1 to infinity of x greater than A minus 1 over n. So you can think about that. A here, A minus 1, A minus 1/2. Okay. So you can see the cross interval, right? This interval. So you see that A infinity is the intersection of A minus, okay? So it's the intersection of the open interval there. Okay. And so actually, so this implies that the inverse mapping of, so that x in A infinity, we know this is actually the inverse mapping of this interval. Okay, and so this is inverse mapping of the intersection. Okay. Now, by proposition 4.1.a, the inverse mapping and the set operation is commutable. So this is the intersection. Okay, and so finally, this is, but this inverse mapping is described in this way. That's why I write down here directly. Okay. And because this event, this type of event is in F, okay? So every event here is in F, so their intersection is also in, so that is in F2. By the third property of sigma algebra we discussed in chapter 2, right? So by the third property, okay. This is by the second property, okay, the second property of sigma algebra, and this is by the third property. Okay, so if you need, I can make right by the second property. And this is by the third property of a sigma algebra. Okay, so we have that. There, there's one more. One more types of semi-infinite interval. 3 x in okay. So this is x less than a. Less than a here. And so it's the union x less than or equal a minus 1. Okay. And what is that? A here. So a minus 1, a minus 1/2, etc. So that this is sage. So you can see that is the union of the closed semi-infinite interval. Okay, because as n go up, the right endpoint go into A, but always less than A, right? And it go up. So the union never reach to A. So that's why you have the opening end here. Okay, so from this you know that this semi-infinite interval is the union of this semi-infinite interval. Yes?
Why you can use the second item because the third one is the second one's complement.
Oh, yeah, that's good. Yeah, That's better, yeah. Thank you. All right, so yes. Okay, that's great. Yeah, maybe that is better, but this is, even though this is still true. Complement, that's true. Yeah, thank you. And so this is implies that x is less than a is in F. So this is by the second property of sigma algebra and the 2. Okay, because we proved that this is in F already. That's good. Thank you. And fourth, X is in half open, half, in the open interval. That's great. All right, so this is equal to, okay, and so you can see this is x less than b intersect x greater than a. All right, so that it is the intersection that x less than b and x greater than a. But x greater than a is already, by our assumption, it's in F, and x less than b is this type, right? It's already in F. Okay, so this is implies that in F. Okay. So this is the intersection of two events of interest in F. So this is also in F. 5. A, half open, half close. So this is, all right, and so this is x less than b intersects x greater than a. Again, so this is implies that. Okay, so this is intersection of the event of the types we have proved before. Okay, so this one, this type, is in F, and this is in F. And the sixth one, so this is x less than b intersects x greater than or equal to a. All right, so F, and finally okay. Right, so we check the other 7 types of intervals. There are only 8 types of intervals, right? And we just say that one type, this type, for this type of interval, that is an event in F, then we can show that the other 7 types of intervals, okay, these intervals, they describe an event of interest in F2. Okay. All right, so now we recall a real valued function g of x of a random variable x, okay, can be regarded as a data processing of the measured random data x on outcomes in S in the sum space, right? Okay, so now we will answer the question that if we do some data processing on a random variable, actually on the value measured by the random variable x, right? By a real value function g, all right? Then this composition, all right? This composition function, this is still a random variable, okay? So this is the very basic question we should answer. Okay, so we let G be a real value so that the codomain is the set of all real number. It's a real value function on an interval I, okay, which contains the range of a random variable x. Okay. But to be able to do the data processing, we need the requirement that the range of the data processing function, the domain should contain the range of the random variable. Okay. All right, so now how do we know that g of x, okay, so this is also is a random variable too. Okay, so this is all. All right, and so the answer is on an intrinsic property of the data processing function G. Now, by proposition, the proposition we just proved, 5.2.a, the composite function g of x, we know is here. Okay, so it's a composite function. Okay, it's a random variable. If and only if for all a in R, g of x greater than a must be in F. Okay. So this function, because it's just a function, right? It's a composite function of the function capital X and the function of g. So it's a composite function only. Okay. All right, and from this proposition, okay, so this composite function is a random variable if and only if that this subset of the sample space is an event of interest in F. Now, since all right, this event, this subset says that g of x, okay, is in A infinity. Okay, so that this is the inverse mapping of A infinity okay. Okay, so let's see here. Inverse mapping here. And as we know, the inverse mapping of the composite is equal to the composite of x inverse and g inverse. But you have to reverse the order. Okay, and so this is x inverse of g inverse. Here. Okay, so what is that? Okay. So this is subset of the sample space, which is specified that the composite function has value greater than a. It's the same as to specify by random variable x here, okay? So that x is in this set, okay? Right? Since this one, and x is a random variable. Then g of x greater than a, it's so now this is in F if this one is a Borel set. So it's a Borel set in R. Okay? So if this is a Borel set in R, now x in B must be an event of interest in F. Right? Okay. So the important thing is that if the inverse mapping of this simple inverse in the open interval is a Borel set in R, then this is an event of interest in F. Okay, so thus if for all A in R, the inverse mapping of G of A to infinity is a Poisson set in R, then G of X is a random variable. So we find sufficient condition. So we found sufficient condition. Okay? So that is sufficient. Okay. So on Thursday, we will examine functions G which has this property. Okay, because if a function G has this property, then for sure that G of X must be a random variable with this. Okay, right? Any questions? So if no, then I will stop here.